Hello physics students. Now I'm very excited for today because what we're going to be doing is we're going to be deriving the expressions for current as a function of time in an inductor. And what that means is differential equations. Now you may remember the process for deriving the current as a function of time in a charging and discharging capacitor. And you may remember that that process was pretty lengthy, but it was also very elegant and beautiful, and it led to some interesting equations. The same thing's going to happen with inductors. But before I jump into the mathematical detail, what I first want to do is go over how an inductor works, what it is, so that you have a firm root of the physics before we jump into the detailed math. Now, remember at the start of this topic that any coil can be used to induce voltage from Faraday's law and Lenz's law. So if I take this coil, which is just a spring, and I bring near it a bar magnet. Well, I don't have a bar magnet on me, but suppose this marker's a bar magnet. When I bring this, say, north pole to this coil, a voltage gets induced. And then when the magnetic field is a constant, there's no voltage induced. But when I pull it away, I'm changing the magnetic field, or I should say the magnetic flux in the coil, BA cos theta. I'm decreasing that voltage induced. So whenever the flux changes, there's a voltage produced and possibly a current. But I don't need a bar magnet, because if I pass current through this coil, it makes its own magnetic field. And then if I try and change that magnetic field by changing the current in the coil, voltage will be induced. In other words, if the current's steady, there's no effect of the inductor. But as I try and increase the current, that's going to increase the flux, which will induce a voltage backwards to make that increase lag. So I'm trying to force current to increase, but it's not shooting right up, it's sort of gradually rising. A same effect or similar effect happens when I try and decrease the current. So I got steady current, no effect. But then as I try and decrease the current, I'm decreasing the magnetic field and therefore the magnetic flux. There'll be a voltage induced to oppose that. So the decrease is opposed. The current is driven in the forward direction, so it can't drop instantaneously. It has to gradually decrease. So an inductor acts similar to mass in a mechanical system. Push on a piece of paper, it takes right off. Push on a car, and now it's going to lag. So the mass of the object is similar to the inductance in a circuit. All right, so that's how an inductor works. Now we're going to go into deriving those expressions. As I said, means differential equations. But before I go into the details, I first want to review the process we took when we were studying capacitors. That's actually why I'm close to the camera, so that the board behind me is going to be out of focus. Because what I want to ask you is, do you remember the 4 main steps of these derivations? They're going to be the same. Can you remember them? Because this process is lengthy, can easily fill up a page. You can't memorize it all, but if you memorize these 4 main steps, the 4 signposts, it'll help guide you toward that elegant solution. So I'll create a pause, see if you can list the 4 steps in your mind. All right, hopefully you said that step 1, you create a differential equation using Kirchhoff's loop rule. Step 2, you separate the variables. You put all the current terms on one side and all the time terms on the other. And then you integrate both sides, and then you solve for the current. So again, Kirchhoff's loop rule, make the differential equation, separate the variables, integrate both sides, solve for I. So let's take a look at how that process works. Okay, so what we have is a basic circuit like this with a voltage source, a switch, a resistor, and an inductor. They're called LR circuits for obvious reasons. Here's the loop rule. Remember I said when we were studying circuits that imagine yourself to be a little ant with a little tiny voltmeter walking around this circuit in the direction of current, tallying up the voltages along the way. Your answer will be 0. So the little ant walks through the battery from the negative terminal to the positive, so it goes up the emph of the battery. Comes around in the direction of the resistor, it goes through the resistor downstream to a lower voltage, so we put the minus. V equals IR from Ohm's law. I'm going to use a lowercase I in this example. And then we get to the inductor. As we learned yesterday or in the last video, the voltage in an inductor is negative L di dt. So we've made a differential equation. Again, that does not define current. It defines the derivative of the current. And we've got to now go through the rest of the way to find out what the original function current is. So we separate the variables. Actually, I forgot. Remember back when we were studying capacitors, I said that this is a math expression that says something. To people who know how to interpret math, they can look at this and deduce the answer without even solving. Let me show you how. So this is a detour, by the way, not part of the curriculum, but very useful for possibly later in life when you're studying higher math or engineering or modeling of very complex systems. You often can get a lot of information by doing a sort of conceptual analysis of an equation like this. So let's suppose I as a function of time. When this switch flips down, we know the current was 0 in the beginning. In other words, this term doesn't exist. And so what we could see, if this is to be equal to 0, is that this term has to balance out this term so they add to 0. What that means is that we need a positive derivative to our function. Because if it were a negative derivative, we've had negative, negative, so we'd have some positive number plus another positive number, could never equal 0. So the derivative must be positive, so we have plus minus something equals 0. So that means our function starts up like this, okay? Another thing, the bigger L is, the smaller the derivative is, so this equality holds. So a larger inductance would begin like this, okay? But let's say we got a small inductor, so we have a high slope. Next, that means some later time here, the current is no longer 0. This term appears. That means that these two now negative create the 0 to the nth. That means that since this now has appeared, this term has to get smaller, which means the derivative had to have gotten smaller. So I'll draw a line of lesser slope. But that still means that later the current is even greater. So this term got even bigger, which means this term has to get even smaller slope. But more current, again, less slope. And that keeps happening, that this gets bigger, meaning less slope, until eventually we get to the smallest slope. And then this term vanishes. In other words, the slope is 0. And I must be nth over r. So when you multiply by r, you have nth minus nth. So not only do we know the shape of our graph, we also know its final peak value. And we never solved anything. Beautiful stuff. Just being able to think mathematically and understand how a differential equation works. Again, not part of the curriculum, but I find it a lot of fun. And by the way, if this were a larger inductor, it would still peak out at current nth over r, but it would start like this and it would just take way longer to reach that final nth over r. Larger inductor doesn't affect the final value. It just means it'll take longer to get there. Interesting, interesting. At least I think so. All right, so this is what we're going to expect. That 1 minus exponential, that's ultimately what we're going to get if you remember from capacitors. Let's move on now. Separating the variables. I'm going to add this to the other side, to the 0 side, and it leaves me nth minus IR. All right. Let me create a pause to allow you to copy this down if you need a moment to catch up. moving on. Now, notice we still have not separated the variables. I and t are on the same side. So I'm going to move the dt to the other side, and I have to move this I over here. But we never separate variables by adding IR in differential equations, because what would happen is we would not be able to integrate that. We've got to, at this point, only divide or multiply terms. So we're going to divide by this entire term to get it to the other side. And what that leaves is 1 over here, but I'm going to move the dt to the other side also and divide both sides by L. Now I have the variables separated. All current variables are on one side, all time are on the other. The constants can go wherever I want, but that's essential, I, and t over here. Third step, integrate both sides. So I'm integrating the current from 0 in the beginning to some current value at some other time from 0 to t final. So the right side, dt, 1 over L's constant, so that doesn't affect the integration. But dt just integrates to t over our limits. That's pretty easy. But this integrates, it's kind of like when you're integrating di over I. That would integrate to natural log. But we have this extra minus 1 over r because of this negative and this r term here. You could do a u substitution to figure that out. I don't recommend it because the solution is going to be long enough. I would just recommend to try and remember that, that you got this negative 1 over r here for our limits 0 to I. Finally, step 4, we have to plug in our limits and solve. So on the left side, we plug in capital I first, and then we plug in 0. Now, a word of caution. A lot of people see this 0 here and they just say, okay, minus 0. No, it doesn't mean 0 is the second term when we plug in our limits. Kind of a common mistake. Plug in 0 for I, and you see that you have this, not 0. And then t final and 0 limits, and that's pretty straightforward. Notice I also multiplied the negative r to the other side to put it together with the inductance. Let me create a pause to allow you to catch up if you need a moment. All right, let's move on. So what we could do is we could combine these two natural logs because of the minus. We combine them as a division inside the log. And then this, of course, I'm just going to drop the t final here just to make it more convenient. Now, how do we get, again, we're solving for current right here. It means we got to get rid of the log. So what we do is we take the e function and we put all of this into the e function and all of this into the e function, giving us this on this side, but e to the log, the e and the log gone, and it just leaves us the argument here. And then the rest is just multiplying m to the other side, adding IR, and then factoring out the m and dividing by r, and there's our expression, that 1 minus function. Remember, this term begins at 1, e to the 0 is 1, and then as time goes to the infinity, e to the minus infinity is 0. So the exponential goes from 1 to 0. So what we have in parentheses here is in the beginning 1 minus 1, which is 0, and eventually 1 minus 0, which is 1 times m over r. And so there's our expression in the pattern. Another reminder, in capacitors, we defined something called the time constant. And for capacitors, the time constant was RC. But for inductors, it's L over R. And then you could write the exponential this way if you wanted to. Again, what that means is that the function responds more slowly the bigger L is. That's what I said before, right? If bigger L starts with a smaller slope, it can take longer to get to the final value of m over r here. And the smaller the resistance is, then the bigger the time constant also. Because the smaller the resistance, the higher the final current is, it's going to take longer to reach that higher current value in the end. So a lot of concepts. Wow, this is a very rich, powerful, dense expression. All right, let me create a pause to allow you to catch up if you need a moment to copy these notes down. All right, well, we've only gone through half the fun today because the other half is we have to now derive an expression for the current in the capacitor as we try and reduce the current back to zero. Okay, so this is when we started the current at zero, flipped it, and then the current had to rise. Now we're going to derive an expression when the current has to fall back down to zero. So let me make some room. Oh, you know what I would recommend? Go into your notes and make sure these steps are nicely highlighted. Again, the main signposts, you want to have these in your mind to guide you to that solution. So again, separate those or circle those to allow you to, emphasize those. All right. Hopefully this glare on the board from the window is not going to cause too much of a problem. I guess I'll see later when I upload the video. All right, what kind of circuit would this... All right, here's one kind of circuit you could use. All right, so here's the resistor, the inductor. What you could do is you could flip this switch into position A, and then that will allow current to build up in this loop over here. And eventually we're going to have some I0. And then what will happen is we flip this down into position B, and therefore this part of the loop is gone, and all we have is an inductor and a resistor. So that's what we analyze. We follow our steps again. I erased it. Step 1. Can you name it? Hopefully you can. Hopefully you're saying, I know what that is. It's use Kirchhoff's loop rule to generate a differential equation. So again, the way we use Kirchhoff's loop rule is we put a dot here and we imagine we're a little ant walking around our loop, tallying up the voltages as we go around with a little tiny voltmeter. So, loop rule. So our answer will be 0. And the ant walks around, encounters the resistor, goes in the direction of the current through the resistor. The voltage it would register is minus IR. And then it goes through the inductor. The voltage it registers is minus L di dt, the voltage in an inductor. Once again, this, you can figure out the pattern of the answer, the solution, by just analyzing this differential equation. So, we start with some initial current in the beginning. So this term is not 0, but this term and this term have to add to 0 on the other side. So what that means is that in order for this expression to be true, the derivative of the current has to be negative. So we have a negative negative, which makes a positive term combined with the minus IR equals 0. So that means our function starts down like this. Furthermore, the bigger the inductance, the smaller the slope. So this would be for a larger inductor. But let's say this is our function. So at some later time, the current is now smaller. And that means if this term is smaller, this term has to be smaller, which means an even smaller negative derivative, absolute value. So the slope is less negative, which means that at some later time, there's less current, which means if this is smaller, so is the derivative. And so this continues, this getting smaller and the derivative getting smaller until the current reaches 0, at which point the derivative is 0. So this will asymptotically approach the t-axis current 0. Again, I figured that all out without any solving, just interpreting this beautiful, elegant math formula. Second step, can you name it? Hopefully you're saying, I know what it is. I have to separate the variables. Okay, so step 2. So I'll move this term to the other side, and that gives me positive L di dt minus IR on this side. All right, so before I go on, what I want to do is create a pause to allow you to copy this down. Let me stand over here and try and block the beautiful sunlight, but hopefully it makes this a little bit more legible. So go ahead and copy those notes down. Okay, so let's continue on. All right, so what I'm going to do is move the L and the dt to the other side and then divide both sides by the I. So that leaves me on this side di over I. And then on the other side, minus R over L and the dt also. Do you remember the third step of our process? Hopefully you're saying, I know, it's that I integrate both sides. Okay, so that's where we're going next. So this time we're starting at I0 and going to some I final. Now, of course, the current goes to 0 eventually, but what we're looking for is the intermediate values. So we have a function like this, but for the current dropping down. We have di over I, and on this side, the minus R over L constants. So I could just say 0 to t final dt. Okay, so the left side, real simple, natural log. And the right side even simpler, dt just integrates to t. Fourth step, hopefully you're saying, I know what it is. We solve for current now. Plug in the limits and solve. So on the left side, we'll have ln of I, right? And then this minus this ln of I0. On this side, we still have the constants of minus R over L, but the limits of t final minus 0. All right, moving on. So we could combine these two natural logs into one natural log by having I over I0 inside one log. And then, well, this term, once again, I'll drop the t final and just call it minus R over L times t. Again, we're solving for I, so that means we've got to get rid of the log. We could do that by taking the exponential function and putting this inside of it, which just leaves us I over I0. And then we have to do that to the other side, both sides, so that leaves e to the minus RL over LT. Just move the I0 to the other side, and we have our final expression. Okay. So again, if you plotted this on a calculator, or maybe you just know from math, it starts at I0. When you plug in times 0, the e to the 0 is 1. So we have I0. and then it drops gradually. Okay, so once again, we see that for greater inductance, oh, by the way, we could write e to the minus t on tau, where tau is L over R. So the greater the inductance, the more the time we're dividing by a bigger number. That means a larger time constant. That means this function will take a long time to get to zero. Remember I said from reading our differential equation that the bigger L is, the smaller the initial slope is, the smaller negative value. So that means that this will take a lot longer to reach zero if L is bigger or the time constant is bigger. But if R is bigger, then that'll make a smaller time constant, and that'll allow the current to drop more rapidly with a larger resistance involved in the decay circuit. So there it is, the solutions to these differential equations and the creation of these differential equations. I want to close by reminding you again, there are 4 steps here. You should be able to name them. When this video is done, close your eyes. Keep studying these 4 steps until you can name them and feel like even after an hour, you could still name those 4 steps. And then once you can do that, just boom, boom, boom out of your memory, it's pretty likely that you'll be able to make these solutions on your own. Use the loop rule to make the differential equation. Separate the variables, means all the i's on one term, all the times on the other. Integrate both sides, and then solve for the current, the 4 steps. All right, so the homework tonight will be just using these equations. The derivations, you're probably not going to be doing much for derivations on the AP, on the homework, but you can on the AP. This is part of the AP. Sometimes you don't do the whole solution, the whole derivation. They ask you to write the differential equation, and that might be part A of a long problem. Just making the differential equations. So that's something to look out for. But the homework tonight in the book will be mostly just taking these formulas and plugging in what you know and solving for unknowns. All right, I hope you enjoyed the video. I hope you enjoyed the beautiful physics and the math. And I'll see you in the next physics video.